Welcome back after the break, and we're busy looking at magnetic declination. I've just shown you before the break where you can go and look for this information on your map. Now this is your topographical map, as you can see over here, and usually you will find it on the bottom of your topographical map between your references. They will give you the information. There's your other references. But let's quickly go and have a look at what this information means. Now, if you look at the example in the next slide, this is the exact same information that I just shown you on the pole map. It shows you two angles, true north and magnetic north. And we're going to discuss it now, why there's a magnetic north and true north. And then the information that we are going to use to calculate magnetic declination, it shows us the mean magnetic declination is 23 degrees 53 minutes west of true north. And that was when the map was drawn in July 2002. The mean annual change is 6 minutes west. Now annual means yearly. And this is just the people who supplied the magnetic observatory. But very importantly, you need to pay attention over here, west. Now if you look on the timeline, you study the timeline in grade 9. Now the equator separates the northern from the southern hemisphere, and the Greenwich separates the eastern from the western hemisphere. When we move west, we add up. When we move east, we subtract. Just keep this in mind when I'm coming back. And when we look at magnetic declination, we work with degrees and minutes. Now I want you to remember the following. If that's 23 degrees, 33 minutes, it works like time. The degrees can represent the same form as an hours. So let's say, for instance, this is 33 minutes. So our next minute is going to be what? 34. So let's say, for instance, for argument's sake, this was 23 degrees, 59 minutes. Where is it going to next? Remember, it's only 59 minutes in. There's only 59 minutes in an hour. In this case, there's only 59 minutes in a degree. So if we have to continue with an extra minute, what's going to happen? We're moving over to 24 degrees, 0 minutes. Keep this in mind. I will explain it again in the next slide. So if you look at the mean magnetic declination, it shows 23 degrees 33 minutes. Annual means it changes 6 minutes westwards every year. Let's quickly look at the information. True north is true north. This is found at the North Pole. The magnetic north is the direction that the compass will point. The MD is the magnetic declination. It's the angle that we are going to calculate. It's this angle over here that we are going to calculate. And very importantly, if you look at the next set of information, the 2002-06 refers to the year and the month that the declination was recorded. In this case, it was recorded in 2002, and July is the 7th month. So that should be, if you look at the next page, should be a 7. but we're only going to use the year, the 2002. So this 2002 are we going to use to determine the annual change. If you look at the next bullet, 2000 to 2005 refers to the years the map maker used to get the mean, the average magnetic declination. Now we are not going to use these dates. You are only going to use the first date when it's been recorded, to the year and month when the declination was recorded. So it doesn't matter which map you receive, you're only going to use the date there. Not the month, only the year. Only the year, in this case 2002. And the mean annual change refers to how much the magnetic declination changes by year, and the change is in minutes. As you can see the symbol that we use over here, like the 23 minutes, that's degrees, 32 minutes. The declination can change west, and that increases. That's the reason why we add. Or it changes in an easterly direction, where we're going to subtract. Now let's quickly go and look how we're going to calculate magnetic declination. So this is the map of pole. Let me just quickly clean up here a bit. You will see that the map of pole shows us the following. And I want to go back to your topographical map so that you can get familiar with this. The mean magnetic declination is 23 degrees 53 minutes west of true north during July 2002. The annual change is 6 minutes west. So that's the information that we're going to use. So already we know it's traveling west. What happens with west? It's going to increase. If that was east, what's going to happen? It's going to decrease. And I'll show you now. So if you look at magnetic declination, so the question will state, calculate the present magnetic declination. Now the present magnetic declination refer to what is present, 2017. That's our present year. So we want to know what is the present magnetic declination for the year 2017. Now we've seen that it's moved 6 minutes west. So let's continue doing the calculation. So what is the mean magnetic declination? It's 23 degrees. The magnetic declination is 23 degrees, 33 minutes. And when they did the magnetic declination, it was in the year 2002, July 2002. The annual change means every single year it moves 6 minutes west. So we want to calculate the present magnetic declination. So what do we need to do? Every single year it's moved 6 minutes west. So we need to get the difference. Once again, same as gradient. If I've got 10 apples and you've got 5 apples, what's the difference? 5. You subtract the lowest from the highest. In this case, 2017 minus 2002, because that's when it was recorded. And that gives us an answer of 15. Am I right? Let's go and work it out to make 100% sure. 2017 minus 2002 give us an answer of 15. Now every single year it's changed 6 minutes. Now from 2002, so what we need to do? We need to take that 15 and we times it with the annual change. That's 6. So let's just move up a little bit. So 15 times 6 equals 90 minutes. Now remember, 6 minutes. 90 minutes equals how many hours a minute? Put it this way. 60 minutes equals 1 degree. So 90 minutes is going to equal what? 1 degree and 30 minutes. How did I manage to get that? Because if you take 90 and you subtract 60, because 60 minutes equals 1 degree. Now, like I've mentioned to you before, because it's moving west, what are we going to do with that 1 degree and 30 minutes? We're going to add it to the magnetic declination. Because it's moving west, we're adding. So in this case, what are we going to say? 23 degrees, 33 minutes, plus 1 degree and 30 minutes. Now, pay attention, we've added over here. Why? Because it's moving west. So 23 degrees, 33 minutes, plus 1 degree, 30 minutes. It's going to give us the answer of, let's do it over here. Very importantly, 23 degrees plus 1 degree gives us 24 degrees. But 33 minutes plus 30 minutes gives us how many minutes? 63 minutes. But 63 minutes equals 1 degree and 3 minutes. So 23 degrees, 33 minutes, plus 1 degree, 30 minutes, equals 25 degrees and 3 minutes. Because 33 minutes plus 30 minutes gives me 1 degrees and 3 minutes. And that's the reason it's not 24, but 25 degrees and 3 minutes. Okay, let's quickly go over this again before we're going to do another example. The mean magnetic declination was 23 degrees 33 minutes. And they recorded this magnetic declination during 2002. The annual change, it means it moves 6 minutes west. And because it's moving west, we're going to add it to the magnetic declination. So we want to see what's a present magnetic declination, so we need to take our present year of 2017 and we subtracted when they recorded the mark, 2002, and we got a total of 15. Now, every year changed 6 minutes, but we need to calculate the present magnetic declination. So we need to take that 15 times 6, and we got 90 minutes. 90 minutes equals 1 degree and 30 minutes, because 1 degree equals 60 minutes. And because it's moving west, we add the magnetic declination to the annual change over the years. 23 degrees, 33 minutes, plus 1 degree, 30 minutes, equals 25 degrees and 3 minutes. Stay tuned after the break Then we're quickly going to do a couple of more examples so that we can make sure you are 100% ready for this question during your final exam. See you in a bit.